In this video, I'm going to be reading from the beginning of Chapter 5 from But Where is the Rainbow? This is the section in the book where I debunk the evidence for time dilation and length contraction, and I'm sure that many people who read the book will want to skip to this chapter because they'll be very interested to see how I do this. When writing this book, I employed a two-pronged approach. On the one hand, I focused on exposing the latent contradictions and flaws that are hidden within special relativity. And on the other hand, I focused on promoting my own theory as an alternative. And I think it's necessary to do both of these things at the same time. Because if I just focused on criticizing special relativity, then it's natural to just think, well, okay, special relativity is not perfect, but do you have a better idea? If you don't have a better idea, then I guess we just have to accept special relativity, in spite of its flaws. And if I just focused on my theory, then probably very few people would take it seriously because they think, well, we already have a perfectly good theory that has nothing wrong with it, and so there's no room for any other explanations. And that's why really you have to do both at the same time. You can't just pick one or the other. In this chapter, I dispute the evidence for time dilation and length contraction. However, I should also mention that even if it turns out that length contraction and time dilation are real, that's not actually fatal to my theory. The reason I say that is that my theory doesn't actually say anything about time dilation or length contraction. It doesn't forbid them, it just doesn't predict them. So, if time dilation and length contraction turn out to be real, then that really gives special relativity a boost over my theory, and it makes my theory look relatively weak by comparison. Some of the big themes that will come up in this chapter are circular reasoning, accepting statements as true by definition, interpreting quantum mechanical effects as relativistic effects, interpreting the effects of acceleration as the effects of inertial motion, and the unfalsifiability that comes from taking advantage of the freedom to choose how to interpret both a theory and the data after collecting the data. Chapter 5: Empirical Evidence and Predictions. Falsifiability and risky predictions. I have adopted the view of scientific progress that was dominant in the 20th century, after having been established by Karl Popper and Thomas Bayes. According to this view, the currency of scientific credibility is only earned through prior exposure to the danger of genuine attempts to refute a given theory. Theories that have been protected from the risk of refutation have less scientific credibility, while theories that have been exposed to real challenges and have survived attempted refutations will gain enhanced scientific credibility. According to Karl Popper's view, a scientific theory is characterized by risky predictions, and a theory that cannot be refuted is one which is unfalsifiable and therefore pseudoscientific. Related to this is the idea that a useful explanation must also be a useful prediction, and that the reward of enhanced credibility must be tied to the risk of refutation. Along similar lines, Thomas Bayes introduced a rigorous mathematical and statistical framework where one updates the probability that a theory is true over time through a process of conjecture and refutation. It's no accident that Bayesian probability theory has been applied to many fields, including stock market trading. For precisely the same reason that a gambler is not permitted to place a bet on the outcome of a sports game after the result has already been determined and publicized, a theorist should not be permitted to determine what results their pet theory predicts after the relevant data has already been collected and analyzed. To the extent that the advocates of a theory are permitted to cheat by having access to the evidence in advance, the status of that theory must be demoted from scientific to pseudoscientific. If what a theory both predicts and forbids is not perfectly clear and precise in advance of a consideration of the evidence, then it must not be considered to be perfectly clear and precise after a consideration of the evidence either. Making use of the data prior to deciding how to interpret both the theory and the data is akin to engaging in insider trading. Regrettably, it has become trendy in science to talk about the prediction of a theory when the more appropriate term would be post-diction. A post-diction would be like a prediction, except that it does not manifest until after all of the relevant evidence has come in. A post-diction is only able to account for what we already know because of its impressive hindsight. In recent decades, the word predicts has come to be used as a shorthand way of saying is consistent with. In other words, the theory is consistent with the observations, even though the observations were never actually predicted in advance. The effect of this misuse of the word prediction is to give unfalsifiable and unscientific theories an air of scientific credibility which they do not deserve. Karl Popper also provides an insightful and eloquent account of how formally scientific theories can transform into pseudoscience. According to Karl Popper in Science as Falsification, some genuinely testable theories, when found to be false, are still upheld by their admirers. For example, by introducing ad hoc some auxiliary assumption, or by reinterpreting the theory ad hoc in such a way that it escapes refutation. Such a procedure is always possible, but it rescues the theory from refutation only at the price of destroying or at least lowering its scientific status. As we will see, all of the evidence that has thus far been amassed to support inertial time dilation and length contraction comes from a combination of circular motion and circular reasoning. I will also demonstrate that the supervelocity and selection theory of light is a genuinely scientific theory by the standards of Karl Popper. The supervelocity and selection theory of light makes clear, testable predictions, and it is falsifiable. Empirical evidence for time dilation and length contraction. Magnetism and length contraction. An electromagnet has been frequently cited as an experimental verification of length contraction. Both Edward Mills Purcell and Richard Feynman have popularized the idea that the previously observed phenomenon of magnetism can now be retroactively explained as a consequence of special relativity. Magnetism is often falsely cited as a prediction of special relativity, even though it is merely, at best, a post-diction. The basic idea is that if you have negatively charged electrons moving relative to positively charged atomic nuclei, from the frame of reference of the electrons, the atomic nuclei are compressed together in the direction of relative motion. This compression makes it appear as though there are more atomic nuclei than electrons, and therefore there must also be an overall positive charge. Meanwhile, from the frame of reference of the atomic nuclei, it is hypothesized that the electrons must appear to outnumber the atomic nuclei, resulting in an overall negative charge. In other words, you can obtain both a positive and a negative charge from nothing, and this would necessarily violate the principle of conservation of electric charge. But let's imagine that this account is true, and that because space has shrunk in the direction of motion, a larger number of particles will appear to fit into the same amount of space. Would this necessarily affect the overall electric charge? Wouldn't particles and their relative influence also shrink accordingly? For example, if you shrink the size of an atom, wouldn't its mass also shrink? Why wouldn't it? Why wouldn't the amount of charge per particle also shrink in a similarly relativistic way? It just does not follow logically that we should expect the overall charge to increase, such that an imbalance between negative and positive charges is created by relative motion. Furthermore, it is important to note that the electrons in an electromagnet are not moving in an inertial frame of reference. Rather, the electrons are moving around in a circular path, and I will explain why that's important later. Even if it may look like there are more electrons from a certain perspective, the actual number of electrons can be counted, and this number has not actually changed. Because you always have the same number of electrons moving around in a circle, and double counting these electrons cannot be permitted, then from a more global and comprehensive perspective, it really does not look like the number of electrons has increased at all. If we assume that the elementary particles themselves adopt perspectives at all, then why should we assume that they adopt an incoherent local perspective as opposed to a comprehensive global perspective? Why should elementary particles be so easily duped? The science of working out how it is that elementary particles perceive reality, if, in fact, that is what they do, is still in its infancy. We don't and can't know how the elementary particles digest information, how they decide what to pay attention to and what to ignore, or how they go about making decisions. Elementary particles are the simplest things that we can imagine, and so their cognitive processes are obviously very difficult to model. The bottom line is that the total number of electrons is necessarily conserved, and so is the actual ratio between the electrons and the nuclei, and this conservation must be reflected in the overall charge that is measured. Therefore, length contraction cannot explain the magnetic force. However, it is perfectly fine to accept the rules of electromagnetism as brute facts, which require no deeper explanation. It is much better to have no explanation than it is to prematurely accept a pseudo-explanation. Because magnetism has been studied long before the theory of special relativity was proposed, this necessarily means that special relativity did not predict magnetism. At best, the idea that magnetism is caused by length contraction is an awkward, post hoc explanation of the sort that characterizes pseudoscientific reasoning. Muons and time dilation. Muons are elementary particles. You can think of muons as like electrons, except that they're about 207 times as heavy and are relatively unstable. Muons only exist for extremely short periods of time before they decay. The reason that muons have often been cited as confirming evidence of inertial time dilation is that it has been estimated that atmospheric muons are able to cover a frame-dependent displacement of more than 20 kilometers during their short half-life. Because muons have a half-life of only 1.56 picoseconds, then the size of this frame-dependent displacement would imply that the muons must be traveling at a relative speed that is at least 5 times that of the speed of light, relative to Earth's frame. Inertial time dilation is used to explain how muons can survive long enough to make this 20-kilometer trip without moving any faster than the speed of light, relative to Earth. The idea is that the half-life of the muon must be dramatically extended due to inertial time dilation. The argument that I've just outlined undoubtedly relies on circular reasoning. Without availing ourselves of the assumption that it is impossible to exceed the speed of light, then we cannot interpret this evidence in a way that supports time dilation. We must first assume that special relativity is true, in order to construe this evidence in a way that lends support to the same theory. Alternatively, if we do not first assume that special relativity is true, then the same evidence actually falsifies and refutes special relativity. By way of an analogy, suppose that a relative of yours had a pet theory about the moon, and that according to this theory, the moon sits at an altitude of 20 kilometers. Under the assumption that the moon must be 20 kilometers away, your relative can then use the moon's visual angle to calculate a lunar diameter of only 180 meters. Now that your relative knows that the diameter of the moon is 180 meters, they can combine this information with the observed visual angle of 0.5 degrees to confirm that the moon is indeed 20 kilometers away. While circular reasoning does demonstrate a degree of internal consistency, it is not a cogent means of supporting a scientific theory, because it can also be used to validate any theory, irrespective of how accurate that theory is. When a circular argument is the best argument available, this is a sign of an extraordinarily weak theory. Simply knowing the length of the frame-dependent displacement of an object with an unknown velocity is not enough to determine either its relative velocity or the time interval. We also need to know precisely what its relative velocity is in order to use the Lorentz equation to calculate the degree of time dilation. We cannot work backwards from the length of the path taken by the particle in order to calculate either the velocity or the time dilation without making additional assumptions about its velocity. By first assuming that the time dilation is occurring, in order to draw an inference about the relative speed of the muon, and then using this relative speed to conclude that time dilation is present, we would be engaging in circular reasoning. The misconception about the speed of light as a universal speed limit, which I have previously classified as Hydra head number 6, has been used to revive the entire beast. The simplest explanation for the surprisingly long frame-dependent displacement of the muon is that muons are capable of traveling at superluminal speeds. Hence, it would be simpler and easier to conclude that special relativity has been refuted in two ways with just one observation. In other words, no time dilation has been observed, and the speed of light has also been exceeded. When the velocity of atmospheric muons has been measured directly, researchers have often found that these particles do seem to be moving at faster than light speeds. But under the dogmatic assumption that superluminal speed is impossible, these anomalous results are normally ascribed to calibration or measurement error and adjusted accordingly. Particle accelerators and time dilation. Particle accelerators and colliders move extremely small and light subatomic particles such as hadrons at very high speeds. To observe relativistic effects, specialized synchrotron particle accelerators are used, which confine the particles to a beam that navigates a circular track. What the circular shape of this track necessarily means is that the particles are not in inertial motion relative to Earth. Instead of inertial motion, these particles experience accelerated motion as they oscillate back and forth. Incredible speeds have been achieved in synchrotron particle accelerators. The particles are apparently able to complete several thousands of laps every second, on a track which spans several kilometers. We can say that the speeds attained are very fast indeed, but because the particles are not moving in a straight line, we cannot say that inertial motion is what is being manipulated or measured. Inside a synchrotron particle accelerator, acceleration is a confounding variable which cannot be disentangled from inertial motion, and I will explain why this is important later. Atomic clocks and time dilation. The infallible atomic clock. While a broken clock is right twice a day, an atomic clock is right always, and no matter what, by definition. In my view, it was a mistake for the International Committee for Weights and Measures to sanctify the atomic clock in 1967 by setting the definition of the second to exactly 9,192,631,770 oscillations of the cesium-133 atom. This change in the definition of the second has meant that the atomic clock has been the standard by which time is defined and measured ever since. It is officially inconceivable that atomic clocks could be prone to error or bias. In the Hafele-Keating experiment, atomic clocks were mounted onto supersonic jets and flown around the world in order to measure mere nanoseconds worth of time dilation. It was hypothesized that traveling against the rotation of Earth would result in a gain of time, and that traveling with the rotation of Earth would result in a loss of time relative to a clock that is on the ground. These assumptions raise interesting metaphysical questions, which are worth exploring in more depth. Earth's rotation is angular momentum as opposed to ordinary inertial motion. This means that it forms a flat disk in velocity space, and only the center of this flat disk represents the overall location of Earth in velocity space. The width of the disk represents the speed of rotation, and the plane of the disk represents the plane of rotation, which is perpendicular to the axis of rotation. However, for increasingly short intervals of time, angular momentum also becomes increasingly indistinguishable from ordinary inertial motion. Therefore, if inertial time dilation is real, then time dilation should also apply to angular momentum. But the rotation of Earth is absolute. We can objectively determine what the absolute speed of Earth's rotation is, as well as the axis and direction of rotation. It is not equally plausible that Earth might be stationary and that the rest of the universe might actually be revolving around it, which was once the dominant view. Therefore, the angular momentum of Earth seems to be an absolute in some sense. But yet, angular momentum is also relative in another sense. Angular momentum is always relative to a specific axis in position space and to a specific point in velocity space. If we are considering the question of to what degree Earth is rotating about its axis, and to what degree the rest of the universe is rotating about Earth's axis, then it's important to remember that this axis will be the same axis in either case, because it will have the same location and orientation in position space, and it will also have the same location in velocity space. Through focusing on the point of contention, Earth is revolving versus the rest of the universe is revolving, it is easy to lose sight of the agreed set of facts: the position and orientation of the axis of rotation, its location in velocity space, and the absolute magnitude or speed of rotation. So in this situation, there is not really much of a disagreement at all. It is simply more parsimonious to assume that the reason that the axis of rotation just so happens to pass directly through the center of the Earth, and that it just so happens to match the precise location of Earth in velocity space, is because this axis of rotation is a property that belongs to Earth specifically. This has been a bit of a digression, but I think that it was necessary to explore how these difficult and deep philosophical questions apply specifically to the results of the Hafele-Keating experiment. Even though the axis and the speed of the rotation of Earth is an objective fact, and even though Earth's axis occupies an objective point in velocity space, the point that Earth's axis occupies in velocity space is still no more special than any other point in velocity space. This point in velocity space cannot be considered motionless in any absolute sense. Many other objects may occupy this point in velocity space, but for different reasons, and it cannot be claimed that these objects are objectively motionless just because they share the same location in velocity space. It still does not matter where we decide to place the zero in velocity space, because all locations in velocity space are still presumably equal. Hence, it makes no sense to assume that by moving around the axis of Earth in position space, and by occupying locations that differ from Earth's axis in velocity space, one is really moving in any objective or absolute sense. The symmetry cannot be broken so easily. The only objective variable in the Hafele-Keating experiment arose from the fact that the plane that flies with the Earth's rotation covers more distance in velocity space than the plane that flies against the rotation of Earth. In this case, covering distance in velocity space translates to experiencing the force of acceleration. The independent variable that was measured in the Hafele-Keating experiment was merely the degree of acceleration experienced by various atomic clocks. The experimental hypothesis in the Hafele-Keating experiment was confirmed, but it is important to note that in this case, the path of motion was circular, only the force of acceleration was actually being measured, and that the only standard for time measurement used was the rate of oscillation of a cesium-133 atom. Satellites. Time dilation effects are observed when communicating with satellites, which also rely on atomic clocks. It has been alleged that there is both a gravitational and an inertial motion-based effect that is observed when the satellite-based atomic clocks start to drift out of sync with ground-based atomic clocks. The supervelocity and selection theory of light also predicts that some apparent inertial time dilation should be observed with satellite communications, but for a very different reason. According to the supervelocity and selection theory of light, the signals that are received either by the satellites or by the transmitters on the ground are actually part of a superwave which traveled slightly faster than the speed of light relative to the sender, but at exactly the speed of light relative to the receiver. These signals must be very slightly redshifted, which gives the impression of a slightly slower oscillation rate, and a slightly slower atomic clock speed. This also means that the electromagnetic signals that the satellites receive from Earth have reached them slightly faster than we would expect them to, and the same applies to the signals received on the ground. Overall, this makes the atomic clocks on the satellites appear to be running relatively slowly, but this is mainly due to redshift, and the effect is incredibly subtle. The claim that the atomic clocks on GPS satellites experience time dilation from inertial motion carries with it the implicit assumption that only the orbital velocity of the satellites matters, and not its direction. Multiple satellites may orbit Earth at the same speed and at the same altitude, but in different directions. This means that in addition to moving relative to Earth, the satellites are also moving relative to one another. But the tacit assumption is that the satellites which orbit at the same altitude, and therefore the same speed, will also share a common inertial frame of reference, even if they are moving in opposite directions. I've already demonstrated the problem with this line of thinking in the Twin Paradox 2.0, but I will revisit it briefly. If the satellites are understood to be moving relative to Earth, but not relative to each other, then it follows that their time should be dilated relative to Earth, but not relative to each other. But there's no reasonable basis for the idea that satellites which orbit in different directions are not moving relative to each other. The satellites that orbit Earth in different directions are also moving relative to each other. Therefore, if special relativity is true, then we should also see time dilation between the satellites themselves. But because there is no asymmetry between the satellites, this also creates a paradox. There's no way for us to determine which satellites should be further ahead and which should be further behind. If something is causing the atomic clocks to slow down at high altitudes, then it can't be inertial motion. The total distance covered in velocity space is the only variable that is being manipulated in this case. Common themes in the purported evidence. You may have noticed a few recurring themes in the evidence that has been provided in support of special relativity. Firstly, all of these purported examples of time dilation and length contraction rely solely on observations of quantum objects. We do not have any confirming observations with respect to classical objects, such as golf balls, planets, or people. Classical objects are a very broad category. Secondly, with the notable exception of muons, all of these effects depend on accelerated and/or circular motion, as opposed to linear and/or inertial motion. In my view, it is not reasonable to generalize from the observed effects of acceleration on quantum objects to the effects of inertial motion on classical objects. There's no good reason to expect that classical objects should behave exactly as quantum objects do at high relative speeds, but there are many good reasons to expect that classical objects should behave differently from quantum objects at high relative speeds. Ideally, it would be necessary to perform controlled experiments in order to determine how classical objects respond to extreme acceleration, how quantum objects respond to extreme inertial motion, and how classical objects respond to extreme inertial motion. I have represented what the empirical evidence has demonstrated to date in this chart. The box with the check mark indicates that there is empirical evidence of time dilation for quantum objects, which are in circular and/or accelerated motion. But in order to truly confirm the predictions of special relativity, all four of these boxes would need to contain check marks. The ultimate confirmation would be an observation of inertial time dilation with respect to classical objects. The other two boxes represent the intermediate steps, which have also not been tested or confirmed yet. What cesium-133 atoms, muons, hadrons, and electrons all have in common is that these are quantum objects. The behavior of quantum objects is radically different from that of classical objects because they obey the laws of quantum mechanics as opposed to the laws of Newtonian mechanics. The vast gulf between the behavior of quantum objects and classical objects is universally recognized, irrespective of whether the Copenhagen, many worlds, or pilot wave interpretations of quantum mechanics are favored. Briefly, it is neither the size nor the mass of an object per se that gives it a special quantum mechanical character. Quantum mechanical properties appear to result more directly from the degree of isolation of an object from its environment. A classical object is well integrated with its environment in a way that a quantum object is not. This integration is known as entanglement in the quantum mechanical lexicon. Due to their isolation, quantum mechanical objects retain a number of freedoms that classical objects do not have. Even though we label these quantum mechanical objects as particles, it is more useful to think of them as waves. In other words, out of necessity, we have been systematically conflating a quantum mechanical effect with a relativistic effect. While the distinction between classical and quantum objects is really more of a continuum than a binary category, treating this distinction as a binary category works adequately for our present purposes. In my second book, I will dive much deeper into the nature of the division between classical objects and quantum objects. It is easy to understand why it is that we've never been able to experimentally manipulate and examine the effects of extreme relative speeds on classical objects. We simply do not have the technological capacity to accelerate a classical object, such as a bullet, to relative speeds in excess of 100,000 kilometers per second. By comparison, a typical bullet moves at a relative speed of less than 1 kilometer per second. The other common theme amongst the various examples is that inertial motion is never held constant and manipulated independently from acceleration. The original research question was about how relative inertial motion affects the relative rate of the passage of time for classical objects and classical observers, such that the observed speed of light is held constant. Unfortunately, the electrons, hadrons, and cesium atoms all travel along a curved path and are subjected to constant acceleration. Perhaps applying a force of acceleration and/or gravitation has an effect on the rate of oscillation of these wave-like quantum mechanical objects, which is then mistakenly interpreted as a relativistic effect caused by their inertial motion. Not only can this quantum mechanical interpretation not be ruled out, but it also seems to be the most plausible interpretation that is available.